Hello everyone and welcome to our webinar about electric vehicles test systems. My name is Thomas Hanchin. I'm a product manager at Enetic CTS based in Rheinach, Switzerland. I'm responsible for our test solutions for harmonics, flicker, as well as electrical test equipment. For electric vehicles, this covers electronic power sources, analyzers for harmonics and flicker, as well as other accessories that are used for the tests. The webinar will take about 25 minutes. We will have some time at the end for the question and answer sessions. The presentation will cover mainly 3 parts. The first part is an introduction to electric vehicles. The second part is about standards, the most relevant standards in the electric vehicle environment. And the third part is about, or will be about testing specific tests of electric vehicles. So let's start by having a look at the electrical circuits on an electric vehicle. Shown here in the 3 colors, green, blue and red, are the 3 electric circuits. There is the light blue, which is the so-called low voltage 12 or 24 volt circuit, which is the traditional electric circuit of cars. Then in addition to that, on an electric car, we have the red electric circuit, which is everything that is related to high voltage. So this is the electric circuit that drives the car. So it eventually supplies the motors with energy. It supplies also the traction inverters, the braking system, and the energy actually comes from a battery. So the high voltage part is actually the driving energy of the electric car. Now, in addition to that, we need something to charge the electric car, obviously. And this is shown here in green. So this is the so-called AC, alternative current charging system. So it might be the onboard charger, plus in addition, the external, for example, off-board charger or external infrastructure that is required. So in an electric car, we have 3 different electric circuits. Now let's have a look at the different standards. Now I tried to split it up into the 3 sections, 3 electric circuits, green for AC, blue for low voltage and red for high voltage. In addition, I split it up into the international standards and regulations, as well as the manufacturer standards, because there might be quite strong differences in these 2 segments of standards. Now, at first, let's have a look at the low voltage standards. Now, there are many manufacturer standards. Each car manufacturer has developed their own standards over the last 20 years, I would say, or so, 25 years. We have, just as an example, in our test library, you have over 30,000 test cases, which shows how broad this whole manufacturer standard world is. Now, for the low voltage section, there are very well-known documents as international standards and regulations. For sure, there's the EC Reg 10, which we'll cover later, as well as the ISO 7637-1-2 and additional standards. There are more ISO and also IEC standards that apply here. I just show here 2 examples, probably the 2 most important examples. Now on the high voltage side, the situation looks a little bit different. So we are still at the beginning of the standardization. So there are 2 ISO standards that apply today. One is the 21498-1 and -2, which we'll cover later. Another one is the ISO 7637-4 series. So also this we will have a short look after or like later in that presentation. So these 2 are international standards, are the only ones that exist for the high voltage components on a car. For the manufacturer standards, we have a little bit more. So I show you like some examples of standards that exist already. So that's mostly European car manufacturers that have developed their own standards, maybe their own tests as well. There is one specialty here. It's the LV123, which is one common document that some car manufacturers from Germany have worked on, where they define a common set of tests that need to be performed on electric cars. Now, LV123 doesn't exist as a standard as it stands, but it is now implemented in manufacturer standards, such as the Mercedes MBN 11123. Now, if you go to the AC world, there are manufacturer standards. I show some examples here. And then there are SAE and DIN or EN or ISE standards. The ones I show here, they are all focused on charging stations. So they define the digital protocols, they define the compliance tests that need to be performed, etc., etc., etc. Now, the dominant document for LV and the AC world is the ECREG 10, which we will cover later. But basically, ECREG 10 is a United Nations law or United Nations regulation that cross-references to very well-known other ISE standards, which I show here. And these ISE standards are there since, I would say, decades, and regulate the green, so the AC world, the world of the energy provider. Now let's jump into one or two examples of international standards for high voltage components. I'm going to show you a short introduction into the standards as well as the tests. Let's have a deeper look at the ISO 21498. So it's a standard and it's the first standard for high voltage components. It is meant for the voltage class B systems, so that's everything above 60 volt up to about 1500 volt DC. This standard is split into two parts. Part 1 defines voltage classes and subclasses and characteristics of high voltage components, and Part 2 defines electrical tests for high voltage components. It is a very new standard. It is currently being voted on, and the published plan is for 2021. So next year, it's going to be released if everything goes well with the final voting. As I said, it's for Class B electric propulsion systems. And as far as I heard and know, it is well supported by all major car manufacturers. And this leads me to my assumption that this ISO 21498 will be the main and the most important standard for high voltage components in the future. It defines similar tests as LV123, slightly different, but very, very similar tests. Now, we spoke about voltage class B, just a short slide about that. So basically, there are two voltage classes defined in ISO. It's voltage class A, which is the low voltage part, up to 60 volt DC, 30 volt AC. And then there's voltage class B, that's what you consider high voltage, and it's everything above 60 volt DC up to 1500 volt DC. Now, ISO 21498 has defined several subclasses for voltage classes. You can see them here on the left, and they range from 220 volt DC up to 1250 volt DC. In addition, ISO 21498 defines also so-called operating statuses. So these are statuses a high voltage component can operate in. Now, we can bring them both together by combining the voltage ranges with the operating statuses, which is shown here in the middle. So each high voltage component has a so-called rated or nominal voltage. It has also a voltage range where it should operate normally, so in the OS1. Then it has an upper and a lower voltage range where it might operate in different operating statuses. And it has an over voltage range up to the over voltage limit, where it might operate even in operating status 4, so with limited capabilities. Now, each high voltage component has an over voltage limit, and these limits are defined by the voltage subclasses. So let's have a look at the different tests that are performed. I prepared here an overview table of the tests, so you can see they're numbered by chapter from 6.2 to 6.11. You can see also the names of the different tests, for example, direct current supply voltage, hour voltage, under voltage tests. Now, I try to characterize or summarize them in a category, which you see in the third column in the type. So you see there are basically different types of tests, or I try to group them in different types of tests. One is the so-called immunity voltage variation test, which we will see an example later on. Then there are some emission tests, so that's what disturbance a high voltage component generates and emits to the electric car. There is a special test called ripple on DC, which we will touch later on as well. Then there's a battery test, and yeah, that's about it. And in the fourth column, you see, or try to summarize which test equipment is required, like DC sources, oscilloscope to measure emission, etc., etc., etc. But we will cover that later on. So let's have a bit closer look on some of the tests. So the first test we're going to look at is the voltage variations. So voltage variations tests the immunity of a high voltage component when it is operated or supplied by different voltages, operating voltages. On the left, you see an example. So the nominal voltage of that component is 350 volt DC. Now the blue range shows the range where it should operate normally, so in operating status 1. Then it has the range B, which is the over voltage range, and it is a range D with an under voltage range. And the top line there is the limit, so it's the over voltage limit, and above that limit the component might break, might fail, might not work properly, so it is like a non-defined state. Now with all the voltage variation tests, and there are different ones defined in ISO 21498, we test the capability of how the component operates in these different, or while these different supplies are there. So there are different ramps defined. I have shown one here, one of the tests. So we basically have voltage ramps with some stable condition at 1 volt operating voltage, then transition times to another stable condition, and additionally some other transition times. Now the stable conditions might be present for several minutes, while the transition times might be in like some volts per second, so very slow changes, or very fast changes with the low dump, for example, which are very fast changes in the 250 volt per millisecond, so some millisecond transition times. The test equipment that is required is basically a source, a DC source, that is capable of providing very stable the supply voltage, but is also capable of doing the fast transition times. Now, nowadays, the border of the nominal voltage is around 1000 volt DC. It might go in the future up to about 1500 volt DC. And the maximum slew rate for very fast signal might be 250 volt per microsecond. In the ISO 21498, actually the fastest pulse that is defined has 250 volt per millisecond slew rate. A second, a bit a special test, is the so-called low dump test. Here it's also a voltage variation, so we apply a special waveform, but with very, very fast slew rates. You can see here the dV over dt is about 250 volt per milliseconds, so this gives a rise time of about 200 microseconds from one operating voltage to the other operating voltage. And the maximum voltage, which is defined in ISO 21498, at least in one subclass, is 450 volt DC. Another test that is performed is the so-called ripple immunity test. Now, some of the electric components on a high voltage bus, like the motor inverters, they generate disturbance signals, disturbance current, usually at the switching frequency of the inverter. And these switching currents, they generate voltage distortion on the DC supply voltage. And this immunity test actually superimposes on the DC supply an AC signal, which the frequency ranges from 10 Hz up to, depending on the standard, about 300 kHz. So we're simulating here the different ripple, current ripple and voltage ripple that might be present on a high voltage DC bus. The test setup consists of a DC source that you can show here, that's our NetWave, for example, and it consists of high frequency signal generator plus an amplifier and a coupling device. Usually this is a inductive coupling through a transformer. So in this case, the NetWave, so that the source supplies DC to the test object, and the amp and the CN, which is the ripple generator, generates the ripple on top of the DC. As I said, the maximum requirements are about 30 volt peak, which is the ripple voltage, which might lead to very, very high ripple current depending on the impedance of the test object. Another important standard, an international standard, is the ISO DTS 7637-4. So it's the newest part of the well-known ISO 7637 series. It was just recently published in May as a technical specification, though it's not a standard, but it's a technical specification, and it's already being applied by test houses and car manufacturers and component suppliers around the world. It also includes some high frequency tests, which I will show. Now, the -4 of this ISO standard has now defined 3 tests for high voltage components. The first one is an emission test, so we're measuring again the disturbance that is generated by the test object. Then the second test is the so-called pulse A. It's a test setup for immunity test for pulse sinusoidal disturbances, and the special thing here is the frequency range from 1 to 10 MHz, so it's a relatively high frequency test. And pulse B, which is the third test, is immunity test for pulse sinusoidal disturbances. So the voltage range here is from 3 to 300 kHz, and it's again the ripple test on DC. So the same ripple test I just showed before is also defined, a little bit differently defined in the -4 here. Now, here's with the details about the special test of the ISO 7637-4. It's the RF pulsed immunity, and you can see here that the ISO standard defines some pulse frequencies from 1 to 10 MHz and test voltage severity levels from 1 to 4, and 4 is like the open case where you can define the voltage yourself. So required for the test setup is again obviously a source that provides the DC, and then we have an RF signal generator, which is shown here in the middle, plus some coupling device. So the coupling device couples the RF disturbance signal on the high voltage DC line. And as I said, it's a high frequency test between 1 and 10 MHz. Now, this concludes the part of the high voltage DC tests. Now let's jump to the AC standards and tests. Now there are many standards. I cannot cover all of them today. Now that's why I focus on one, or on the most important standard, or actually the regulation that apply to AC. Now EC Reg 10 is a United Nations regulation regarding vehicles. It's well known under the E-mark test. So it's similar like the CE tests in the industrial and consumer world. The E-testing is done on full cars plus electrical sub-assemblies. The UN regulation, this UN regulation is a legally binding document, so it's in brackets and quotes, it's the law in most of the countries. And the revision 5 added actually specific requirements for electrical vehicles. And these are the tests that are performed. So you see they are numbered from 7.2 to 7.9 plus 7.10 to 7.19. The first one is for full vehicle, the 7.10 and on is for electrical sub-assemblies. And this EC 10 regulation is defines much wider the requirements for components as well as full cars. So it's not only about the functionality checking and disturbance checking on high voltage components, but it's more like testing the full environment and the full impact of the component or of the subassembly on the environment. And I'm not going to go through the whole list in detail, but you see that there are RF emission tests, there are harmonics, voltage changes, and fluctuations, or as flicker, there's emission on RF, etc. So there's immunity to electromagnetic radiation, etc. So the EC Reg 10 doesn't really define the test itself or like how the test is performed or test setups. It's more referring or reference to other already present IEC and ISO standards. And this is in the third column here. I'm listing the standards, the relevant standard for that specific test. And as well the equipment very broadly that is required. Now I will go into some of the standards. I'm not going to cover all, but I'm going to show some of the tests that are performed according to EC Reg 10. The first test I want to start with is the harmonics test. So this is defined in the IEC 61000-3-2 and -12. As you can see on the top left, that's the test setup. So basically we need a three-phase or single-phase AC source that provides a very clean signal to the test object, which in this case is the car in charging mode. What is shown in the middle there is the measurement device. So it's typically a power analyzer that is capable of measuring harmonics, harmonic currents, and usually also harmonic voltages. So it measures the harmonic emission, the harmonic current emission that is generated or created by the car in charging mode. Typically the voltages that are required are three-phase for 80 volt or maybe sometimes 690 volt line to line. The source needs to be very clean, as I said, so it needs to have a total harmonic distortion below 0.5%. And what is important, you cannot just use any power analyzer, but you need a power analyzer that is according IEC 61000-4-7. That's an IEC document that specifies exactly how the power analyzer needs to measure those harmonic currents. The frequency range are the normal IEC 61000-3-2 and 12 frequency range. So it goes from the mains frequency 50 Hz up to the maximum the 40th harmonics, which is 2 kHz. The second test I want to highlight here is the flicker test or voltage variations. It's a similar test setup then for the harmonics, as you can see on the top left. So again, here we have a source, a three-phase source or a single-phase source that provides a very clean AC signal. We also have a measurement device, which is shown with the little M in the circle there. So the measurement device needs to be, that's the so-called flicker meter, needs to be according IEC 61000-4-15. There also it is very clearly specified how the flicker meter needs to measure. And then the special thing for flicker is actually that we have a so-called flicker impedance. So that's an additional impedance that is introduced into the measurement circuit. And now while the car is charging, it might switch on and off, or might switch to in between different voltage levels. And these like different currents that flow generate voltage fluctuations or voltage drops over that impedance. And these voltage variations are measured by the flicker meter, and there's an interpretation which in the end gives a so-called short-term flicker and long-term flicker measurements. So this is also a very well-known IC 61000-3 series test that is performed on any electric device that is connected to the grid. The technical requirements are set the flicker meter and as well the flicker impedance that need to be according to the IC standards. Now, two additional tests that are performed on electric cars according EC Reg 10 are the surge and the burst test. Now, while harmonics and flicker are emission tests, so we're measuring the disturbance that is generated by the car in charging mode, here this is an immunity test, so we're testing how the car or the charger reacts depending on some disturbance signals that we generate. And the first test is shown here, so it's the so-called burst test according IC 61000-4-4. EC Reg 10 defines test levels of plus minus 2 kilovolt, and it's a standard burst pulse with 5 nanoseconds, 50 nanoseconds, 5 kilohertz repetition rate. The test setup you can see here on the right. So we have again the car in charging mode. We have like a coupling network, the coupling decoupling network, the CDN, which consists of some capacitors, which are the coupling elements, as well as some inductances, which are the decoupling devices. And we have an EFD or burst generator that generates the bursts. Now the surge test is a very similar test, but with another pulse. So it's according IC 61000-4-5. The test levels are for AC charging plus minus 2 kilovolt for line to protective earth, or plus minus 1 kilovolt line to line. If the car is charged into the DC mode, it is 0.5 kilovolt line to protective earth or 0.5 kilovolt line to line. And the test setup is very similar. So we have again a coupling decoupling network, which is shown here on the left. Then you have a surge generator that generates the typical surge pulse, and it is coupled through an 18 microfarad capacitor on the DC or AC line. Now, in the last like 20 minutes or so, you got an introduction to electric vehicle testing. So as a short summary, you have learned that electric vehicles have three power systems. It's the low voltage 12-volt system, it's the high voltage system that can go up to 1000 or 1500 volt DC, and it's the AC mains. Now, there are standards for high voltage components. They exist today, they evolve very, very quickly, because the more electric cars that are developed and sold, the more problems the car manufacturers find, and this usually then reflects into the standards again. And the most important standards I would like you to remember, it's for high voltage, the ISO 21498 and LV123. And for the AC mains, it's clearly the EC Reg 10, referring to other IC standards such as the IC 61000-3-X series for harmonics and flicker, as well as the -4 immunity test systems. So this concludes the presentation. I've received a couple of questions. So the first question was about if I see higher voltage classes than 1000 volt. Yes, there are. It's less for like cars, but more for heavy-duty vehicles like buses and trucks. I see projects up to 1500 volts. Then the second question is, which is, in my point of view, the most critical test to perform? Well, each test has specific challenges, I would say, but the most challenging test for sure is the ripple immunity test. So there, very high or very large currents can occur, ripple currents. So a very small or simple ripple generator doesn't do the job. So we really need quite a big and powerful ripple generator. So that's a very specific test. And then the third question was if there is a standard for railway electrification. Yes, there is a European standard, and I will provide the exact standard name in the email we will send out. So this concludes the webinar about electric vehicle testing. I'm very glad that so many people joined. If you have more questions or are interested in our products, for sure you can get in touch with us. Either just simply reply to the email you will get, or go to our webpage, amatexcts.com. So thank you very much for joining. I hope to have you back in one of our next seminars about another topic. Thanks, and have a good day. Bye-bye.